Asdeep Thaplial from Atmospheric and Oceanic Sciences Group at Space Application Center, Ahmedabad, and today I will be discussing about hyperspectral remote sensing of atmospheric parameters. Today's lecture will be slightly different from the other lectures we have been hearing for so now, because other lectures were dealing with the hyperspectral remote sensing in the visible and near infrared region, whereas I will be discussing the remote sensing in the region of infrared, that is from 4 micron to 15 micron for the atmospheric observations. So first I would like to discuss the importance of satellite observations, why we require hyperspectral remote sensing of atmosphere. We know that we depend upon weather forecasting in our day-to-day life for the weather information during next hour or the next day or maybe for next week or next month, for planning of various events. For these type of weather forecasting, the weather forecasters require information on atmospheric temperature and moisture profiles throughout the globe, and this information we get from a satellite. Before the satellite era, the temperature and humidity profile, that is the white water vapor profile in the atmosphere, were obtained using weather balloons. You must have seen, if you have visited a weather observatory, some meteorological observatory, that they launch a huge balloon filled with gases, hot gases, and when the balloon rises up in the atmosphere, it is fitted with an instrument which records temperature and humidity at various atmospheric levels and then transmit it back to the ground station. And this information is used to predict weather at that location. So that is the common conventional method to acquire the atmospheric temperature and humidity profile information. Now these type of informations are very limited. They are limited to very few land stations. The satellite plays a very important role in this field because it provides the information on atmospheric temperature and humidity profiles equally over entire globe. The first satellite that provided the vertical profile of atmosphere, that is the sounding, was Nimbus satellite, which was launched in 1969 by US. Since then, the satellite instrument technology have improved significantly, and during past decade we have seen launch of now the first satellite which was launched for atmospheric profile retrieval was Nimbus in 1969 by US, and during last decade we have seen that many new satellite instruments have come up for the observation of atmosphere, and hyperspectral infrared sounding is one of them. This slide shows you the distribution of radio sound network, the balloon which I just discussed, that how we launch a balloon fitted with the instrument to measure temperature and humidity as it rises up in the atmosphere. And these observations are only limited over few land stations. In this slide you can see that these yellow dots, they show the Met Observatory, where we have where we take observation of temperature and humidity in the atmosphere. So you see most of the land regions we do not have these observations, and these observations are almost absent over vast oceanic regions. So they are highly localized over land regions, and added to that, these observations are taken only twice per day, that is at 0 and 12 UTC every day over these stations. So this makes it very low density observation over land as well as ocean. So forecasters need the information over the entire globe, including oceanic region, because you know that the weather over India is affected vastly because of the moisture which is coming from the ocean. You know, monsoon season, we get a lot of moisture from the Arabian Sea, that is the monsoon current. We get depression as well as cyclone which is coming from the Bay of Bengal, the monsoon, the depression or the monsoon forms in this region and moves into the land region and provides a lot of rainfall. So we depend on satellite for information about atmospheric temperature and humidity over these regions which are inaccessible for the humankind. Now these satellites have played a major role in this connection by providing vital information on atmosphere from space. You see there are many satellites in orbit launched by various countries. You will find here the Indian satellite INSAT in this region, which makes the observation of cloud imagery over Indian region. But that is only to provide you cloud imagery and derived wind, and from which we can derive wind speed and some other meteorological observations. But we do not have Indian satellite which can provide us the information on temperature and humidity profiles. In fact, India is planning to launch INSAT 3D in geostationary orbit in the INSAT series of satellite that will have a sounder to provide continuous coverage of temperature and humidity profile over Indian atmosphere. Now presently we get these, such information from global satellites, polar orbiting satellites such as NOVA satellite launched by USA and METOP satellite launched by EUMETSAT European country. Now what are satellite products available for the atmospheric parameters? Here is a list describing these. Over atmosphere we get temperature profile, moisture profile, winds, clouds, aerosol, earth radiation buzzard, precipitation, ozone. Over ocean we have surface temperature, ice cover, surface winds, color, sea level, and over land we get information on vegetation condition, snowpack characteristics, and various other land characteristics. Here I would like to mention that these parameters which I have underlined here, they are obtained through the sounder, infrared sounder on board a satellite platform. And this is a roadmap of IR sounding, how IR sounding has developed from multispectral, that is few channels on board this GOES satellite or NOVA ETOPS satellite. There were only about 12 channels, to GOES satellite that is on geostationary orbit having 18 channels, and then the AIRS atmospheric infrared sounder, which is on board Aqua satellite. This has around 2400 channel. The ERC infrared atmospheric sounding interferometer, which is also in low Earth orbiting orbit, it has about 8400 channels. So these are hyperspectral sounders, and the first such sensor was launched in 2002, that is AIRS. ERC was launched in 2006, and this CRIS, which is on board NOVA polar orbiting satellite and POSE NPP, and this has around 1400 channels. The future satellite which has GITS, which has a hyperspectral sounder on board, are GITS, geostationary infrared Fourier transform spectrometer, and hyperspectral environment suite, which will be on board American satellite GOES. So these are the future satellites, and this is the state of art we have till now. And of course we will be launching in 2012, and we will be launching INSAT 3D, which will have 18 channel. That will be very similar to GOES sounder, having 18 channel for making atmospheric sounding. Now I will briefly describe the remote sensing of atmospheric parameters. So we know the dominant radiation which is available in our this terrestrial system is solar radiation. That is in the short wavelength region from 0.1 to 3 or 4 micron, and this solar radiation gets reflected by Earth atmosphere, that is reflected from Earth surface, as well as it is reflected by the cloud top. and part of it gets scattered from atmospheric gases or atmospheric aerosol, and this also gets scattered back to space. Now this is the solar spectrum which you have dealt so far in your hyperspectral course. Now I will be dealing with the thermal radiation. I will be dealing with the infrared radiation which is emitted by the Earth's surface and atmosphere. This is not available through solar radiation because there is less than 1% the radiation available beyond 3 micron in solar spectrum, and during night time there is no solar radiation. So the entire this spectrum, this radiation which is emitted through land surface as well as its atmosphere is emitted spectrum. Okay. Now here I show a spectrum, an infrared spectrum emitted by Earth surface and its atmosphere, and which is reaching at satellite, that is at the top of the atmosphere. So if you make measurement, if you consider Earth as a black body at a temperature of 300 Kelvin, the Earth's emitted radiation would look like this curve, which is the Planck black body curve. But as this radiation which is emitted by Earth's surface, when this reaches the top of atmosphere, it interacts with the atmospheric gases, and atmospheric gases have the absorption of these radiation, and you can see that there are various absorption bands in the atmosphere. CO2 absorbs in the wavelength range of about 4 to 6 micron. Then about 6 to 8 micron we have strong absorption due to water vapor. Then there is absorption band due to ozone, that is around 9.8 micron, and then there is a big absorption band which is due to CO2 in 12 to 15 micron region. So these various gases are absorbing the radiation which is emitted by Earth's surface, and instead of this type of curve, we receive at the top of atmosphere this type of spectrum. And based on the observation of this atmospheric radiation in various wavelengths in this absorption bands, we make observation of CO2, water vapor, ozone, CO2, because we know that in absence of these gases we would have received this radiance at the top of the atmosphere by satellite. But because there is a loss of radiance, there is absorption of radiance which is proportional to the quantity of CO2 in this region, proportional to water vapor in this region, proportional to ozone in this region, as well as CO2 in this region. So based on these measurements of radiances in different spectral region, we can make measurement of various atmospheric gases as well as the temperature profile, because if we know the amount of CO2, then the only reason why our radiance is increasing or decreasing is because of atmospheric temperature. I will discuss this in little detail in my further slides. Now, what causes these absorption? Why we have these type of absorption in the atmosphere due to these gases? We have to understand this before we go to the hyperspectral remote sensing. We know that in atmosphere we have various gases like carbon dioxide gas, water vapor, ozone, oxygen, methane, etc. These gases exhibit vibrational transition as well as rotational transition in infrared region. For any layer of the atmosphere, molecular absorption determines the layer emissivity and transmittivity. So we must understand in various layer of atmosphere how these gases interact with the radiation, whether there are vibrational transition or rotational transitions. In this slide, I will just show you one spectra which is obtained from the Ayer's hyperspectral sounder. And in this one, if I want to describe, if there were only vibrational lines, if there were no rotational lines due to different gases, our spectrum would look like this green line. There would be a broad absorption band at this region for CO2. Then there will be a absorption band due to ozone, and this absorption band due to water vapor. But actually what we receive at the receive the spectrum is like this. If we just blow up this small region, the spectrum will look like this one. Why we have these small absorption lines here embedded in the vibrational band is because of rotation of the molecules. So the rotation is superimposed, rotational transition is superimposed on the vibrational transitions, and that is why we get these type of absorption lines embedded in a wide absorption band. And our multispectral sounder or multispectral imagers, they make the measurement which is averaged over a wide spectral band, maybe of the order of 2 micron to 3 micron. And in that case, all these rotational lines, they get averaged out, because if you are making observation from this region to this region, so we are getting average information or average radiance which is emitted by the gas in this region. So we will not be able to make measurement of individual absorption lines. But in hyperspectral sounder, what we are trying to do is we are trying to make observation spectrally, we are trying to make it so narrow that we are able to sample individual rotational lines in this spectrum, and that is the hyperspectral sounding, where we have very high spectral resolution of the radiometer. One example I would like to show here, and that will differentiate between the multispectral sounder to hyperspectral sounder. Multispectral sounder like gauge sounder or nova polar orbiting this ATOP sounder, they have broadband sounders, and this spectrum which you see, the spectrum at the top of atmosphere received by ERC hyperspectral sounder. Because ERC is a hyperspectral sounder, you get all the rotational lines embedded on the vibrational transition. But the multispectral sounder so far used to make observation averaged over this region. This is the sensor response function of multispectral sounders. These are the various channels 1, 2, 3, 4, 5, 6, as well as there are 18 channels in various absorption bands making observation for the atmosphere. But from hyperspectral sounder we make continuous measurement of all these vibrational as well as rotational lines. Now how it translates into sounding of atmospheric parameters. If you were making observation from multispectral sounders where we are only sampling the vibrational bands, so suppose we make observation at this band, at this band, at this point, this point, so there are 4 or 5 measurements at different parts of this vibrational band. So basically we are sampling different part of atmosphere. This part of the band is sampling the Earth's surface, and this one, the absorption at the center of the absorption band, is making observation at the tropopause. So basically we have only 3 to 4 observations for atmospheric profile measurement. But if we go to the hyperspectral sounder where we have high spectral resolution, we can make observation at each of the rotational lines, and by this way we can make thousands of measurements which will give you information about various thin layer of atmosphere, and from that we can derive temperature and humidity profile as well as the other information about the other trace gases. Now I would just like to give example of various multispectral and hyperspectral sounder, how the resolution would translate into the spectrum, the emitted spectrum of the atmosphere. So I would like to give here 3 examples. This ERC is infrared atmospheric sounding interferometer. This is hyperspectral sounder on board mid-top satellite, which has 8,400 channels. This is AIR's atmospheric infrared sounder on board Aqua satellite. It has 2,378 channels, and its spectral resolution is 1.2. ERC has a spectral resolution of 0.2 centimeter inverse. And if we compare these two hyperspectral sounder with the multispectral sounders such as GOOS, HRS and INSAT 3D satellite, which has a spectral resolution of the order of 20 centimeter inverse. So we can see in the slide, this is the spectrum which we received from ERC, having 8400 channels. So we can see here that we are able to get information about each of the rotational as well as vibrational lines in this spectrum. So we can derive much more information about temperature profile, the water vapor profile, and the ozone profile. If we move on to 1.2 centimeter inverse resolution, if we decrease the resolution of hyperspectral measurement, so from 2.2 to 1.2, so here you can see that much of the information is getting averaged. Many of the rotational lines are getting averaged, and the signal is predominantly from this vibrational lines. So there are only few strong rotational lines which we can see here. So this is AIRS and CRIS hyperspectral sounder. Now if we move on to current sounders, which we have on board GOES satellite and no polar orbiting satellite that has a resolution of 20 centimeter inverse. So the spectrum would look like this one. So all the rotational lines which you had seen in the ARC as well as AIRS got averaged out, and the spectrum which you get at the top of atmosphere is somewhat like this. So you can only broadly specify that this is strong absorption band, weak absorption, and no absorption here. This is absorption due to ozone, and this is absorption band due to water vapor. So this will provide much lower information than the hyperspectral sounder, and we will get less information on temperature profile and humidity profile in the atmosphere. So here you can see a comparison of current hyperspectral sounders. AIRS was launched in 2002 on board Aqua satellite. ERC was launched in 2006 on board METOP A satellite, and CRIS is launched recently in 2011 on NPO's preparatory project NPP satellite. You can see here that in AIRS and CRIS we have most of the regions we have no data. There are only the hyperspectral sounder is making observation in only in few regions, because the aim of AIRS and CRIS is to make observation of temperature and humidity profiles only. So we have this band for temperature profile, we have this band for humidity profile, this one for ozone, and this one also for temperature profile. Okay, and the similar thing we can see in the CRIS hyperspectral sounder, but ERC, where the primary objective is to retrieve temperature profile, humidity profile, as well as the information on the various trace gases such as ozone, methane, and N2O, and chlorofluorocarbons. I'll discuss a little later how many gases we can retrieve from ERC hyperspectral sounders. So we get the complete coverage of the emitted radiation which is reaching the satellite, the top of atmosphere. Now one more aspect I want to discuss about hyperspectral sounder, and that is information content. Now from this satellite you know that there are thousands of channels. We have more than 8,000 channels on ERC, but we are not getting independent information from ERC. We are not getting 8,000 independent piece of information from ERC, or for that matter 2,000 independent information from AIRS, because many of the informations are correlated and they give information about the same level or same layer in the atmosphere. So what is the independent piece of information which we are getting from these satellites, and that we can study that using information content analysis. And we are comparing here the result of GOES satellite, which has 18 channels. This is a multi-spectral, that is a broadband sounder, with hyperspectral sounder typically having more than 2,000 channels. Now if we see for temperature profiles, if we retrieve temperature profile from multispectral sounder like GOES, we get independent piece of information as 2.5, whereas hyperspectral sounders gives you the 14 independent piece of information. And if you compare this with RAOB, that is radio sound observation, you know radio sound is launched from ground based instrument, and it is the most accurate the method for getting temperature and humidity profile observation so far. So if we compare with the information content of REOB, which is 15, the hyperspectral sounder is coming quite close to it, whereas the GOES was giving the information far lower than the radio sound observations. If we move on to water vapor, again we see the independent piece of information was only 2.2, whereas the hyperspectral sounder is giving 8, which is very close to the REOB observation of 10. So this table also tells you that how important is how hyperspectral sounder for atmosphere. Now I will come to the principle of atmospheric sounder. So here I like to describe how a satellite sensor or sounder receives signal which is emitted from Earth's surface as well as intermittent atmospheric layers. So in this diagram, if you see, this is the land surface, and these are various atmospheric layers. We divide the entire atmosphere in various atmospheric layers. Now this is a normal temperature profile of atmosphere at one location. The temperature at surface may be around 300 Kelvin and gradually decreasing as we go up the atmosphere by the rate of about 5 Kelvin per kilometer. And as we reach tropopause around 12 to 15 kilometers, the temperature is about 200 or 210 Kelvin, and then again it decreases in the stratosphere and mesosphere. Now if we try to compute the radiance which is reaching at satellite or the top of the atmosphere, it is a sum of various terms. The radiance which is reaching at satellite in channel number I is equal to the radiance emerging from surface multiplied by its emissivity multiplied by the transmittance of the atmospheric column, that is this parameter, and this is the emissivity of the land surface. Then we have to add the contribution of the first atmospheric layer, which is shown by this term. So this is the temperature of this layer, and this is the Planck function, that is the radiance which is emitted by this layer multiplied by emissivity of this layer, and we multiply by transmittance from this layer to atmospheric the top of the atmosphere. And similarly we have added the contribution from various layers to compute the radiance received by the satellite at top of the atmosphere. Now if we write this equation in an integral form, we get radial transfer equation, which is of this form, that the radiance at top of atmosphere in channel number n is equal to the radiance emitted by Earth's surface multiplied by the transmittance of the atmosphere plus integration over the first layer to the last layer of this product, that is the radiance received by various atmospheric layer multiplied by d tau by dz, and this we call as a weighting function. I will describe you in my next slide what is weighting function, and multiplied by dz. This is the thickness of the layer. Now if we try to understand the weighting function in this slide, the radiance in this this is the radial transfer equation. The radiance at top of atmosphere equal to first term is upwelling radiance from the surface. The second term is upwelling radiance from various layers of the atmosphere, and the last term right now we can ignore. This has very small contribution. This is reflected downward atmospheric emission, so we can ignore for time being this equation, this term, and we only deal with the two terms. Now in this term we find a term which we call as weighting function, and we are trying to understand what is the weighting function. Now if we make observation in various infrared bands in one absorption band, suppose this is CO2 absorption band from 15 to or suppose water vapor absorption band from 6 to 8 micron, and if we make observation at 3 point, here the absorption is very small and here absorption is very large. If we make observation at this point where absorption is very large, at this at this frequency, at this wavelength, the radiance which is emitted by Earth's surface gets absorbed by the atmospheric column, because there is the absorption is very large, the transmittance is very small. So this radiance is not able to reach satellite the satellite height. It is getting absorbed in the intermediate layers. But if we go up in the atmosphere, if we go at the top of atmosphere, whatever radiance is emitted from this, it is able to reach satellite top, because there is no radiance emitted, there is no absorption beyond this point, because there is no gas, there are no gases available beyond this point. So the radiance which is recorded in this wavelength region has a weighting function of this shape. That is, the radiance is a sum of the radiances emitted from these layers, weighted by this weighting function. So basically this weighting function is weighting or multiplying this radiance emitted by different layers of the atmosphere to compute the net radiance which is received by the satellite at the top of atmosphere. Now if we make another measurement at this point where we say that atmosphere is transparent, that most of the radiation which is emitted is passing through the atmosphere and a very small portion of it is getting absorbed. At this point, if we make observation, the most of the radiance which is emitted by Earth's surface is able to reach top of the atmosphere, because only a very small portion of it is getting absorbed by the atmosphere. Now if atmosphere is transparent, that is, if tau is almost 1, it means emissivity of atmosphere will be equal to 1 minus tau, that is close to 0. So most of the atmospheric layers will not be emitting, or will be emitting very small portion of it at this wavelength. So the net contribution at satellite top is received from this layer. So this is the weighting function. So the highest fraction of radiance which is reaching at satellite is coming from surface, and then this is gradually decreasing, and above this layer there is no radiance which is reaching, there is no radiance emitted which is reaching satellite top. So now we can say here that if we make observation at this wavelength, we are basically getting information about the top of atmosphere. If we are making observation at this wavelength, we are basically getting information about the layer which is very close to Earth's surface. And similarly, if we make more observations at various other these spectral regions, suppose at this point if we make observation, this will be giving information about the middle atmosphere. So we can, by this way, we can make a sounding observation at different part of the absorption band to get information about various layers in the atmosphere. Now we want to understand here why we have this bell shape of the weighting function. So you can understand that from here, which I already described, but this is better seen in this diagram, that if we make observation at a particular wavelength, we see that Earth's surface, because the Earth's surface is at very high temperature, it emits most of the radiation, but because of the atmosphere, this is getting absorbed and only this much portion is reaching satellite height. So the weighting function is very small here. If we take intermediate layer, which is at lower layer temperature, is emitting lower radiation, but above this layer the absorption is smaller, so the most of the radiation is able to reach the satellite height. Okay, so this portion we have the maximum weighting function. Again, if we go at the top of atmosphere, beyond this there is very small absorption, but the radiance emitted from this layer is very small, because emissivity is smaller, as well as the temperature of the higher atmospheric layers are very smaller, so the weighting function is very small. So finally we obtain this type of weighting function for each sounding channels. Now, what is the difference between between the weighting function for broadband sounder and hyperaspectal sounder, that we can see from this slide. You know, if we have this type of broad weighting function, it means the radiation emitted is from this broad atmospheric layer. That means we are getting information which is averaged over this layer, this broad layer. But if we make observation at hyperaspectal sounder, which is shown by the this curve, the weighting function is narrower, and this narrow weighting function means that the information which we are receiving from the atmosphere is from a narrow atmospheric layer. So our vertical resolution, the resolution of the vertical atmospheric layers, has improved in hyperaspectal sounder compared to the broadband sounders. So here we can see the comparison of weighting function for multispectral sounder versus advanced hyperaspectal sounders. So we have only 18 channels on GOES sounder, or our Insert 3D future sounder. So there are only 18 weighting functions we can see. So from these 18 weighting functions or 18 radiance measurements, we have to get information on temperature and humidity at different layer of the atmosphere. So we will be getting very coarse resolution vertical information from this type of satellite, whereas we have thousands of weighting functions, and these weighting functions are sharper in comparison to multispectral sounders. So the information which we receive in hyperaspectal sounder is 1000 times higher than the multispectral sounder. So how we make a sounding? How we make a sounding of temperature and water vapor? If we just concentrate on this radiative transfer equation, if we have this equation, if we are making observation at CO2 absorption band, and we consider that CO2 is fixed in atmosphere, that we know the concentration of CO2 is invariable with time, and it is well mixed gas throughout the atmosphere. Currently its level is about 380 part per million by volume. So we know the concentration of CO2, it means we know the weighting function of the atmosphere. So in this equation, if we have 10 or 100 observation in this band, we have 100 radiance measurements. This is known quantity. So only the unknown quantity here will be the surface temperature and the temperature profile. Okay, so we are getting a set of equations where unknowns are Planck function, that is B lambda, B nu Ts, or B nu T. So from these set of equations, we can invert the equation to derive the temperature profile as well as surface temperature, because for this absorption band the weighting function is known because the gas concentration is known to us. Now this will give us the temperature profile. This band will give us temperature profile. If we move on to this absorption band, which is absorption band due to water vapor, if we make a number of observations here, if we make 10 observation or 100 observation in this absorption bands, basically we will have 10 or 100 equations where the unknown quantity will be this weighting function, because the concentration of water vapor is not known. The water vapor is highly variable gas in the atmosphere, and we want to measure that gas using sounding measurement in this band. So in this equation, in this set of equations, the known quantity is radiance, the known quantity is temperature, because temperature profile now we know from this absorption band, which we have already computed from measurements in this CO2 absorption band. So T is known to us, so this function is known to us. Only unknown quantity is tau, that is the transmittance in the different layer of atmosphere. So from this equation, or this set of equations, we can compute the profile of transmittance from various layers for the various layers, and that transmittance or that absorption is proportional to the quantity of the variable gas in that layer. So by inverting these set of equations, we will be deriving the concentration of water vapor in the atmosphere. Now similarly, if we want to compute the concentration of ozone in the atmosphere, we can make observation in this absorption band of ozone instead of making absorption in the water vapor. So if we make hundreds of observation in this absorption band, we will be able to derive a transmittance profile in atmosphere from this set of equations, and that transmittance profile is now dependent upon ozone concentration in the atmosphere, because water vapor has no absorption in this band. So we can invert these equations to derive ozone. Similarly, by making observations in the absorption band of various gases like methane, CO, or CO2, we can derive the concentration of those variable gases by computing temperature from this CO2 band, or by getting temperature information from some other source. But the basic assumption here in the sounding is uniform distribution of emitting gas, and these absorption lines should be non-overlapping absorption lines, and atmosphere should be in local thermal equilibrium. But the inverse problem is not very simple. In this previous slide, I showed you that we can have 100 equations or 200 equations or 1000 equations that is unknown in temperature or unknown in the transmittance profile. But this inversion of these equations becomes ill-posed or under constraint, because the atmospheric profile is not a discrete profile, it's a continuous profile. The temperature, is a continuous profile in the atmosphere. Similarly, humidity also, we have continuous profiles. So we have infinite number of unknowns. The unknowns are infinite, whereas the known quantity, that is the radiance measurement, are finite. That is 20 for around 20 for multi-channel sounder and thousands for hyperspectral sounder. Still, we need there's much more information to invert this equation, because these equations are under constraint. Added to these finite measurements, about 20 measurements from multispectral or 1000 channel from hyperspectral sounder, one problem is that the weighting function of various channels are very broad. So these all observations in different channels are not independent. So if we are making observation in the water vapor absorption band, we are not basically having 3000 independent equations. We will be having only some few tens of the independent equations to derive these many atmospheric layer temperature and humidity. So the problem becomes ill-posed. So to solve these this inverse problem, we need a first guess, and that first guess is obtained through a numerical model. So if we have first guess temperature profile from model or from say regression retrieval, we can derive the final profile of temperature and humidity. So this is a sample observation from GOES, because I cannot show you thousands of observations from hyperspectral sounder. I am just giving you a snapshot of GOES sounder observation. These are the 18 channel imagery of GOES sounders. So this channel is making observation in CO2 absorption band. So basically you are able to see only top of the atmosphere. If you come to this this channel, so this is able to make slightly deeper in the atmosphere. This is the middle atmosphere, this is the lower atmosphere, and slightly you are coming to the surface. So these channels, from these channels, 6 channels, you can get temperature profile at different layer in the atmosphere. These 3 channels are in the water vapor absorption bands, and you can get water vapor profile from these 3 bands, and similarly other bands are for surface as well as atmospheric temperature profiles. So how do we get retrieval equation or retrieval algorithm? Briefly I will describe. I will not go into much detail. If anyone wants to get detail of these algorithms, they can contact me through email and I will be able to help them. So we have to generate a set of training data, and that training data you can obtain through a simultaneous observation of satellite radiances as well as simultaneous measurement of the ray of observation, that is radiation observations. And if you can make that training data set of y, that is radiance, and x, that is the state vector, temperature and humidity profiles, you can establish equation, that is regression equation between these two, and we can derive the regression coefficient, which we can apply to any future observation. If in future if we get radiance observation from satellite, we can use these regression coefficients here and derive the atmospheric profile. So the regression retrieval is very stable, this algorithm for temperature and humidity profile retrieval from sounder observations, but those are not very accurate. So to get accurate information on atmospheric profiles, we have to employ a physical retrieval routine where we make use of the first guess, and the first guess profile is x0, which we have derived from regression, or we can derive this first guess from this model forecast. Now if we minimize, and this y is the radiance measurement in the sounder channels, and this yx is the forward model, that is the radiance which is simulated using a radiative transfer model. So basically there we establish a cost function jx, which is a part which has two parts. First part is minimizing the radiance vector, that is radiance measurement and radiance simulated from radiative transfer model, and the second term is your state vector, and it is the equation is trying to bring this this first guess close to actual profile, which will satisfy our this radiance measurement from satellite. So here I would like to describe the impact of spectral resolution on temperature and humidity retrieval. So if I show you the worst case, which is from GOES sounder or NOVA polar orbiting satellite, the temperature accuracy is shown by this curve, which is about 1.5 Kelvin at ground, and at the best it is about 1.4 Kelvin, and at tropopause it is about 2 Kelvin. The accuracy is not very good. But if you improve your spectral resolution from 20 centimeter inverse to 1 centimeter inverse, your accuracy is reduced drastically, and you are getting very accurate temperature profile. But if you further reduce the spectral resolution to 0.3 centimeter inverse, which is actually the case of ERC hyperspectral sounder, which is on mid-top satellite. So the accuracy of the atmospheric profile which we can receive is this, say about 0.5 K throughout the atmosphere. So we have improved from multispectral sounder to hyperspectral sounder the temperature profile. And if we show the simulation study for water vapor profile retrieval accuracy, so this bottom diagram shows the retrieval accuracy for water vapor from sounders. So this curve is for multispectral sounder, so accuracy is of the order of 30%. Whereas if we move on to hyperspectral sounder with the spectral resolution of 0.3 centimeter inverse, our accuracy is of the order of 10 to 15% for water vapor. So there is a drastic improvement in the retrieval of temperature as well as humidity profile if we move on to hyperspectral sounder. Now I will briefly describe one of the hyperspectral sounder, that is HRS or ERC, how they make observation. ERC is this HRS is onboard aqua satellite, so making across track observations, and it makes observation while it is moving in the orbit, and its path is about 1400 km. Now from here you can see that for 3 by 3 for 9 scan, for the 9 spots of HRS observations, there is one AMSO observation. AMSO is microwave sounder. So for every 9 measurement of HRS hyperspectral sounder, there is one observation of microwave, and that microwave sounder observation is used to remove the effect of cloud on air's measurements, because infrared radiation get affected or get absorbed by cloud. So we have to make observation only in the cloud free conditions. If there are small cloud contamination, cloud patches available in the scene, it will deteriorate your sounding. So to correct that, we make use of AMSU microwave sounding. So similar configuration is also available on board ERC, which is in METOP. So for ERC we have 4 infrared FOV per FOR of microwave. Here in AIRS we have 9. In ERC we have 4 FOV in 1 microwave. Similar for CRIS or ATMS, we have 9 FOV within 1 AMSU or 1 microwave footprint. So these microwave observations are used to clear the cloud effect in hyperspectral measurements. The AIRS coverage, which I already showed you in some of the diagrams here, we can see various absorption regions and the purpose of those observations. This band gives you, because we know that the CO2 concentration is well known, so we get temperature information from this band. This band is used to get water vapor information, this one ozone information, then N2O, methane, water vapor, CO, N2, and CO2. So you can get various trace gas concentration apart from the temperature and humidity profile from IR hyperspectral sounder AIRS. This is sample observation of 1 day observation from AIRS, 1 day of ascending pass. So in 1 day it has make observation almost throughout the globe, and you can see the spectrum, the hyperspectral spectrum in different part of the world. So the spectrum will be different from different regions depending upon the surface type or atmosphere or the vegetation condition or the surface condition. So these different type of spectral signatures can provide you information about various features. This is a list of products which are available from AIRS and AIRS operational agency, and the products are available at 50 km footprint. So there are cloud cleared radiances, which is used for numerical weather prediction as a radiance estimation. We get temperature profile, moisture profile, ozone profile, land sea surface temperature, surface spectral emissivity, surface reflectivity, as well as cloud top pressure, cloud liquid water, and cloud fraction. Besides these observations, we also get the trace gas concentration, carbon monoxide, carbon dioxide, methane, and cirrus cloud optical depth and particle size. So these are research products from AIRS, and these are operational products. But in case of ERC hyperspectral sounder, which covers the entire range of infrared radiation, in that case we even get the operational products of trace gas concentration. This is one sample of the temperature profile which we get from AIRS. The red one is from AIRS and the blue one is from radiosonde. So you can see there is a very close match in observation, the radiosonde observation as well as the AIRS retrieve temperature profile. The right one is for humidity. So you can see here, though the humidity variation in radiosonde is very large, you can see the large variations in different layers. The AIRS does not give that variation because AIRS is a sounder, infrared sounder, and I discussed with you that though there are thousands of channels, those channels are overlapping and the weighting functions are very broad. So we cannot get the small fluctuations throughout the atmosphere, and the information which we get is basically averaged over a thick atmospheric layer, typically averaged over 1 kilometer. So if you average the radiosonde observation at 1 or 2 kilometer, you will see that AIRS closely match with the radiosonde. So this shows a status of hyperspectral sounding right now. This yellow curve shows the accuracy of temperature profile from multispectral sounder, and this blue curve shows the accuracy of temperature profile from hyperspectral sounder. So there is a drastic improvement from multispectral to hyperspectral sounder. These are results of air sounding, and this is for the water vapor. So water vapor has improved from 30% to about 10% in 10 to 15% in hyperspectral sounder. This black dotted lines shows the requirement by weather forecasting agencies. They wanted the accuracy of water vapor to be better than this line and temperature accuracy to be better than this line. And this slide shows that hyperspectral measurements are able to meet the specification which numerical weather prediction agencies require. Now one more example I can show here, that is of low level temperature inversion. If we see ATOPS, that is multispectral sounder, and if we compare the temperature retrieved from ATOPS with the radio sound measured temperature profile, the temperature inversion is not seen very clearly in ATOPS, whereas the inversion is seen very clearly in AIR's hyperspectral sounder. This blue one is AIR's hyperspectral sounder derived temperature profile, and this black one is radio sound derived temperature profile. So if you want to get to study the temperature inversion in the thin atmospheric layer, and that is very important for fog forecasting, we have to have a hyperspectral sounder making observations. Then I will discuss some of the non-traditional sounding applications, and few of them are listed here, that is aerosol detection, volcanic ash detection, cirrus detection, and trace gases. If we make this spectral measurement in this region around 920 centimeter inverse, if we have clear atmosphere, there is no aerosol or dust available present, the spectrum would look like this one, this green line. But if the amount of dust or aerosol is increasing, there we can see a negative slope in the spectrum, and that slope is increasing. So the slope of this this spectrum in this region gives you the size of the dust particle or aerosol particle, whereas this spectrum, the difference between this spectrum to this spectrum and this spectrum and this one gives you the layer of or the level of aerosol concentration from which layer you are making measurement of dust or aerosol. These particles. Dust transport over oceanic region. This is Saharan dust which is transported over over the oceanic region. So two typical cases we can detect from hyperspectral sounder. Then there are sulfate signal for sulfate these particles. If we make a measurement in the difference of these two wave numbers, 1284 centimeter inverse and 1345 centimeter inverse, the difference gives you the amount of sulfate in the atmosphere. Whereas if you make measurement at these two wave numbers, 1228 as well as 995, the difference of brightness temperature in these two wave number gives you the signal of ash particles. So if you see a typical scene in these two this volcanic eruptions, you see that this is the signature of sulfate, whereas this is the signature of ash particles. So these things can be separated, these two can be separated from these two hyperspectral measurements. Now we can make a measurement of trace gases, various trace gases in the atmosphere, and ERC is continuously doing that. So water vapor, so we use the range of 1200 to 1600 centimeter inverse. So this column describes the range of spectral region where we make the observations, and this is the precision of the measurement. So water vapor we can derive with the accuracy of 15%, ozone with the accuracy of 10%, CO 15%, and methane 1.5%. So these are optional products from ERC, and these are semi-operational products, CO2 and volcanic sulfate, HNO3 and N2O, and these are the accuracies. The accuracies may not be very high, but they are very much useful for monitoring regular. If you have a time series of radiances, you can monitor the presence of these trace gases. And these three gases are right now held fixed in the atmosphere, but they can be derived if we make hyperspectral measurements. Some of the applications here we can see, if we monitor time series of air's radiances at different this one. So if we monitor methane, which is we are getting from airs, so there is a seasonal cycle. So we can monitor methane, we can monitor CO, and there is a rise of the CO concentration at this point, which shows that there was some fire event available in that region. So fire event is shown by this type of increase in the CO signal. So this is fire event, this one. And this is the CO2 concentration of CO2, time series of CO2, and this shows the increasing trend in CO2. We all know that CO2 concentration is increasing day by day. And here also you can see that methane and surface temperature, they have the same type of variation, seasonal variation. It means they are linked. The surface temperature is linked to the methane emission. So this type of research you can carry out from hyperspectral measurements. You can also derive the surface emissivity, that is spectral surface emissivity from these type of spectral measurements. If you see seawater, sand, oak soil, oak and ice, the different air's spectrum, you see that there is a lot of difference in these spectrums, and from this type of signatures you can derive the spectral surface emissivity. This is one example I will show here, this very clear example for barren land versus water or vegetated surface. For the red one is for barren land. So barren land, in this part of a spectrum the brightest temperature is high, but as you go to this region the brightest temperature is very small. So there is a difference of about 20 Kelvin when we go from this region to this region. So if there is a difference of 20 K from here to here, you say that this is a barren land. But if the difference is very small, in this case the difference is less than 1 K or 3 K, then we can say that this spectrum may be from water or vegetated surface. So you can classify those type of surfaces from these hyperspectral measurements. And you can also use these hyperspectral measurements to calibrate other broadband sensors such as INSAT VHRR or Kalpana imager. And we have done one small exercise I will describe here, that this spectrum is observed from ERC and this spectrum is observed from airs. And these two, this curve shows the sensor response function of our Indian satellite Kalpana. Kalpana has two bands, one in thermal infrared 10 to 12 micron and another in the water vapor from 6 to 7 micron. So we can calibrate our sensor using hyperspectral sounder. And one small exercise I have shown here, that this is the Kalpana thermal infrared brightness temperature over Indian Ocean, and this is the similar Kalpana thermal infrared radiation which we convolve from ERC, which we average from this measurement. We average over this curve using this sensor response function, and we arrive at this picture. So you see that these two match very close, they are very similar. So it means our sensor is working fine. So we can monitor the radiance observation from various satellites. So this is just one example. We can make continuous monitoring of Kalpana radiances or other satellite radiances with ERC is hyperspectral sounder, and we can conclude here that our observations or the observations from Kalpana thermal infrared or water vapor channel are consistent with time. There is no deterioration in the sensor performance over the time. These are the current satellite, the NPP, which is launched very recently. That is the NOAA NPOS satellite. This has CRIS as a hyperspectral sounder, as well as advanced technology microwave sounder. And by using these advanced sounders, we can derive a variety of land atmosphere, ocean parameters for various type of studies. So this is the state of art from NPOS type of satellites. We can get various products, and the first time we are able to get surface pressure from ATMS and CRIS. Okay, and the performance of current NPP satellite has also improved in terms of data availability. Earlier, polar orbiting satellites were giving you data within 2 hours of observation, but the NPOS and NPP will provide you data within half an hour of observation by satellite. So that is one advancement in the observation. And this is the future hyperspectral sounder. So far, all the hyperspectral sounder which I discussed are on board polar orbiting satellite. So they can make observation twice a day at a particular location. But for weather monitoring, we need very frequent observations, preferably every half an hour. So we need to have a hyperspectral sounder on board geostationary satellite. So GIFT, this geostationary imaging Fourier transform spectrometer, in this is the next step in that direction. And this spectral coverage is very similar to ERC. I'll not go into much detail. And the product which we get from GIFTs are also very similar to ERC. And this is a typical case shown for a cyclone. What information we will be getting from GIFTs geostationary satellite? We'll be getting very high resolution wind information, temperature information, humidity information in the atmosphere, and that will be used by numerical weather prediction models to forecast the course of the cyclone. And this is a summary of my lecture. That hyperspectral infrared observations provide very high vertical resolution and accuracy of temperature and water vapor sounding, and also provide information on atmospheric trace gases. These microwave and infrared imagers are required to provide cloud clearing of hyperspectral sounding observations, which I discussed that ATOPS, we have AMSU as microwave sounder that is used for cloud clearing. Current AIRS and ERC as well as CRIS on board NPOS are providing hyperspectral measurement of atmosphere, and in future we will have two on board geostationary satellite, one on GOES and another is GIFTs. So these observations will improve our medium range weather forecasting and provide important information for climate monitoring. And in advanced geostationary sounder will provide enhanced temporal sampling, and that will improve our knowledge of nowcasting and shorter-range forecast. Thank you. So we have received a question to explain about training data set in regression retrieval. So I would like to describe this slide in more detail. There are two methods to get the training data set. One is after the satellite is launched. If you have satellite already in the orbit and making frequent observations, you can have a satellite radiance measurement at a point, at a place, say New Delhi, and at the same time, because you know what time satellite is making that measurement, at the same time you can launch a balloon or you have reduced one observation from surface that will give you the ground observation of temperature and humidity and other parameters that we call as X, that is the atmospheric profile, and the satellite will give you the radiance Y. So if you have sufficient number of data set over the time, say for example 6 months, the 6 months of time will be sufficient to cover the entire seasonal pattern, and you not only need one data point at New Delhi, but you need several data points spread well over the globe. They should be covered over ocean as well as land and various latitudes. So if you have those co-located satellite measurements along with the radiation measurements of temperature and humidity profile, so we can say that you have a training data set of atmospheric profile X, and you have a co-located data set Y, that is the radiance measurement from satellite. But this is only after satellite is launched. However, if we want to derive a regression or derive regression coefficients before the launch of satellite, so that as soon as satellite is launched and we receive radiance, we start retrieving our atmospheric profile. In that case, what we do is we take the past data set of radio sounding. So this case which I have explained here is one such case where we get thousands of this atmospheric profile during past few years, say past 10 years, and these profiles are obtained from NOAA, ECMWF or various other agencies. So, and these profiles we call as diverse profiles. Diverse profiles means no two profiles should give the same information. They should be different in one aspect or the other. Either they should represent different season, or they should be the wetter or drier atmosphere or some other parameter, but they should not be giving the same information. So if we have that type of diverse profile, say we have 10,000 profiles of radio sonde available with us that has temperature profile, humidity profile, HX. Now what we can do is we do not have satellite measurement at that time. So what we will do, we will use a radiative transfer model that I call here as a function f. That radiative transfer model will be used to compute the satellite equivalent radiance given atmospheric conditions. So this way we can compute the simulated radiances for your satellite sensor for the entire training data set. But we have, because this is using a forward model, that is the radiative transfer model, so we have to add an equivalent noise which is corresponding to your satellite sounder. So if you add that equivalent noise into your forward model simulated radiance, you get a complete data set of X, that is radio sound profile, and Y, that is the radiance measurement. Now this is your training data set. So these are the two methods. One is before the satellite launch, you have to use a forward model, and you have to use a set of radio sound profiles which were obtained during past few years. And the second method is wait for satellite launch and wait for 6 months and gather enough this co-located data set of ground observation and the satellite measurements. So this is the way we can generate a training data set. So this is your answer. If you need further clarification, you can ask again, or you can send me an email, and I'll be happy to provide you with detailed answer. So with this we will complete this lecture, and if you have further queries or any question or any help you need in this regarding this lecture, I'll be happy to answer you. And you can reach me at this email address pk.taplial@sac.isro.gov.in, and this is my postal address. So if you ask me a question, I'll be able to explain that in your mail, or I can send you some detailed literature that will clarify the answer. Thank you very much.